Good afternoon, everyone.
Good afternoon.
Good afternoon, sir.
Good afternoon, sir.
Okay. So let me go to the class directly. So we were discussing crystal field theory. After a brief introduction about the splitting, crystal field splitting, and then about how to evaluate the 10 DQ value, that is the crystal field splitting, through spectroscopic methods. Then we have arrived at the point where we are discussing the factors which determine the crystal field splitting, and those factors were divided into two parts. One is the factors which depends on the nature of the metal ion, and second is the factors which depend on the nature of the ligand. That is the uh, coordinated species. So we have seen that regarding the metal related factors, for a given metal ion, as the oxidation state of the metal ion increases, 10 dq increases. So if you have a ferrous ion and ferric ion, obviously ferric ion will have greater 10 dq value using the same ligands compared to ferrous. Similarly, if I take a cobalt 2 ion, cobalt 3 ion will have higher crystal field splitting in a given with in a given ligand, right, or with some given ligands compared to cobalt 2 plus, right. So divalent, in general, it has been found that divalence ions of the first Transition series, the 10 dq value, or the dq value vary between 700 to 3000 centimeter inverse. That means 10 dq value varies between 7000 to 30,000 centimeter inverse, whereas for trivalent metal ion it increases very much. Dq value is within 1200 to 3500. That means 10 dq value is 12,000 to 35,000 centimeter inverse. So oxidation increase of the oxidation state or the charge on the metal ion leads to increase of the crystal field strength, and we have justified it because crystal field 10 dq value is depending on the nuclear charge, right? Depending on the effective nuclear charge. So if the effective nuclear charge increases, we expect crystal field to increase, crystal field splitting to increase. Then we have also justified why across a period 10 dq increases, because across a period for a given positive charge, say 2 plus or 3 plus, if we go across a period, then the size decreases, effective nuclear charge increases, and because of the decrease in size and increase of the effective nuclear charge, the 10 dq value again increases. And then down the group, the crystal field again increases, and in fact it increases at a much faster rate compared to across a period, and that is because we have seen that again crystal field splitting is proportional to the fourth power of the d orbital radius. So as we go from 3D to 4D to 5D, the d orbital radius increases, and because of the increase of the d orbital radius, the crystal field increases because it is proportional to the fourth power of the d orbital radius. And between first and second Transition series, 10 dq increases by 50%, whereas between second and third Transition series, 10 dq increases by another 25%. And we have also justified that from second to third Transition metal ion, because of the intervention of the lanthanide contraction, the increase of the radius or of the 3 to 4D to 5D orbital is not as much as that is observed for going from 3D to 4D orbital. And as a result of this, we find that for 4D to 5D, the percentage increase is relatively less, whereas for 3D to 4D, percentage increase is much higher. Then we come to ligand related factor. Ligand-related factor. First, we may say about the number and geometry of the ligand. It is found in general that crystal field is dependent on the number of the ligands and how it is arranged around the metal ion. For instance, if you have in general, four coordinated species is if you have a four coordinated metal ion that has got more crystal field than a two coordinated metal ion, and in general if you have a six coordinated metal ion that has got more crystal field splitting than that of a four coordinated metal ion. So as we increase the coordination number, in general the crystal field increases, but beyond 6, the if you increase the coordination number further, the crystal field actually decreases, and this is because as you increase the coordination number beyond 6 coordination number, 7, 8, 9, 10, etc., very often, unless and until the metal ion is very large, what happens that the ligand repulsion increases, because if you increase the coordination number, more number of ligands are spread around the central metal ion, and then with the increase of the coordination number, these ligand atoms comes close to each other and their electron clouds start repelling each other. Beside, there will be also steric repulsion. So in general, with the increase of coordination number, crystal field splitting increases, but this increases from 2 to 6. Beyond 6, if you increase the coordination number, the crystal field start decreasing again, right? And it also depends on the geometry of the ligand. For instance, if you take four coordinate geometry, then if you consider say tetrahedral geometry and square planar geometry, so for both four coordinated you may have tetrahedral as well as square planar, but it is found square planar geometry has got higher crystal field splitting than tetrahedral geometry. So even for the same coordination number, depending on the arrangement of the ligands, sometimes crystal field is higher, sometimes crystal field is lower. Similarly, if you take 5 coordinated geometry, then you may have a trigonal bipyramidal coordination, you may have a square pyramidal coordination. In general, square pyramid has got higher crystal field splitting than a trigonal bipyramid. So for a given coordination number, if the geometry change, the crystal field changes. And finally, finally, we have the charge and size of the ligand, right? It is in general found that as the size of the ligand decreases, that means as the donor ligand has got smaller size, then if the donor ligand has atom is of smaller size, then it can approach the metal ion more closely. So metal ligand distance decreases, and as a result of this, crystal field increases. So decrease of size of the ligand in general leads to increase of the crystal field, and this is nicely reflected by say iodide, bromide, chloride, fluoride. You see, fluoride has got strongest crystal field, then chloride, then bromide, then iodide, right? So as we go across the halogen family, then down the group, crystal field decreases because the size increases. Similarly, if I consider oxide ion and sulfide oxide ion has got much stronger crystal field than sulfide, because again, oxide ion has got the much smaller size compared to sulfide, and because of the smaller size, it effectively interacts more strongly because it can come to the metal ion more closely and it interacts with the metal ion more strongly, and so as the size of the ligand atom decreases, then the crystal field increases. But regarding charge, the thing is not so simple, or it is not very well correlated. We expect from pure electrostatic model that as charge increases, that crystal field should increase, because if you have a say dipositive metal ion and if you have a ligand which is a mononegative and a dinegative, then we expect a dinegative ligand to interact more strongly than a mononegative ligand because of the stronger charge interaction. But the fact is that all of you know, for ligand atoms, as the negative, since most of the ligand atoms are negatively charged, so increasing negative charge leads to greater electron-electron repulsion within the ligand framework, within the ligand electronic cloud, and as a result of this, as charge increases, then the size increases. So charge and size very often act in opposite direction. Increasing the charge very often leads to actually expansion of the electronic cloud of the ligand, and so the size of the ligand increases. And as the size of the ligand increases, very often the interaction decreases, and so effect of charge is not very well documented, or very you cannot systemize the effect of charge. For instance, if you see here in this here you see hydroxyl ion has got -1 charge. On the other hand, oxalate ion has got 2 minus charge, right? So we expect, yes, oxalate has got higher negative, oxalate having more negative charge than hydroxide. You see oxalate has got slightly more crystal field than hydroxide. But then water, having no charge at all on the oxygen atom, it has got stronger crystal field than either hydroxide or oxalate. So effect of charge, sometimes it is observed, but it is not very systematic. The change is not very systematic, and that's why effect of charge is not very well studied, or it cannot be said that it varies in a systematic manner. Now, in general, ligands can be arranged in order of their increasing crystal field strength in a series which is called spectrochemical series. Now, in the spectrochemical series, normally in most of the books you will find the spectrochemical series like this, where as we go from left to right, crystal field increases, right? But there will be some books which writes the series in a opposite fashion. That means in the left hand side we have the ligands with the highest ligand field, and then in the right hand side we have the ligands with the lower crystal fields. But the form in which I have written here, it is the most well documented form. From as we go from left to right, gradually the crystal field strength increases. And this series is called spectrochemical series because I have told you that for a given metal ion, what is the 10 dq value that is generally observed from the electronic spectra of the complexes. So since this series has been obtained experimentally, most of the cases this series has been prepared experimentally based on the spectroscopic electronic spectral data of metal complexes with various ligands. So that's why it is called spectrochemical series. Now in the spectrochemical series, several things you can notice that, as I have told you, iodide, bromide, chloride, fluoride, you can easily see that as the size increases, the crystal field increases, right? You also see that effect of the size of the ligand is also seen, that if you take this thiocyanate, S-bonded thiocyanate can be S-bonded and N-bonded. Now S-bonded thiocyanate, you see it is sitting here in the spectrochemical series, whereas N-bonded thiocyanate, as you can see, it has got much stronger crystal field splitting compared to S-bonded thiocyanate. This is because one of the reasons, there are various reasons for that, but one of the main reason is that the donor atom in S-bonded thiocyanate is sulfur atom, whereas in N-bonded thiocyanate donor atom is nitrogen atom. Now, as all of you know, the sulfur being in the third period, right? So it has got much larger size compared to nitrogen, right? And as a result of this, the metal ligand bond distance in case of N-bonded thiocyanate will be much shorter. Metal ligand bond distance in case of S-bonded thiocyanate will be much larger or longer. And as a result of this, N-bonded thiocyanate produces much stronger crystal field than S-bonded thiocyanate. Similarly, you look at, say, you have nitrite. Now you have the anomaly. You have nitrite and you have the N-bond O-bonded nitride ion, and you have N-bonded nitride ion. Sometimes it is called nitro and it is called nitrite, right? So if you take this again, you find same ligand, but nitrite can coordinate both through oxygen atom as well as nitrogen atom. It is found that N-bonded nitrite has got much higher crystal field than O-bonded nitrite, right? But you will find several things in the spectrochemical series which are apparently anomalous. What is that? I have told you one of them is this: hydroxyl ion, oxalate ion, and water. If you compare, and you can put oxide ion somewhere here also, right? So oxide ion has got a much higher crystal field than hydroxide. So if you take hydroxide ion, mononegative charge, oxalate ion, 2- charge, expectedly oxalate ion or oxide ion has got higher crystal field strength than, or higher crystal field splitting than hydroxyl ion. That is expected on the basis of more negative charge, right? Greater negative charge. But what is unexpected is that water, which is a neutral ligand, it carries a dipole, but there is no charge here. So water, a neutral ligand, has got much higher crystal field than either hydroxyl or oxalate. So this cannot be explained on the basis of pure electrostatic model of crystal field theory, and for that we have to modify our crystal field theory. So spectrochemical series, in a way, is pointing out about some anomaly in the pure electrostatic model, and one of them is anomalous behavior of hydroxyl ion, oxide ion, oxalate ion, and the water. And again, you see acetonitrile, carbon monoxide. These are neutral ligands. Carbon monoxide is actually, it has got very little charge separation in carbon monoxide. From your school chemistry knowledge, you know, in carbon monoxide, carbon and oxygen carries very little charge separation because of the electronic structure of the molecule. But still, carbon monoxide is one of the strongest ligand that is known. So even when it is a very neutral ligand, not only that, carbon monoxide is also a very weak Lewis base, right? So it is neither carrying a charge, nor it has got strong basic character. Still, carbon monoxide is one of the strongest ligand that is known. And again, you see cyanide -1 charge, fluoride also -1 charge, nitride also -1 charge, but they are so different in their crystal field splitting. Cyanide is one of the strongest ligand, whereas nitride, azide, etc., fluoride, they are weak field or moderate field ligand, right? So again, triphenyl phosphine, as you can see, it is a neutral ligand, right? And it has got a very high crystal field strength. So this spectrochemical series throws up certain inconvenient question towards the pure electrostatic model of crystal field theory, and that we have to sort out later on the basis of some modifications of the crystal field theory, or in terms of the molecular orbital theory, right? In terms of the molecular orbital. Then you can also see here that ammonia, ethylenediamine, bipyridine, phenantholene, so many of the neutral ligands, acetonitrile, pyridine, ammonia, ethylenediamine, bipyridine, phenantholene. So many neutral ligands are either moderate or quite strong field ligand, but so many charged ligands carrying -1 or -2 charge, they are very weak field ligand, right? And this cannot be explained properly by the crystal field theory. So the experimental spectrochemical series, in fact, throws up a lot of doubts on the validity of the assumption of the pure crystal field model, where it is thought that the interaction between the metal ion and the ligands are purely electrostatic in nature, and metals and ligands are considered as point charges. That assumption is actually called into question because of this existence of the spectrochemical series. Okay. But you have to somehow remember at least some aspects of the spectrochemical series, arrangement of the different ligands in the spectrochemical series, that you must have to remember this thing to some extent. Then we go to another very important quantity called crystal field stabilization energy, or some books call it ligand field stabilization energy. So if it is crystal field stabilization energy, it is called CFAC, and if it is ligand field stabilization energy, it is called LFAC. So CFAC is the total energy. What is CFAC or LFAC? It is the total energy of the valency d electrons of a metal ion in a crystal field compared to the case when the same metal ions are placed in a spherical field of same magnitude. That means we consider a metal ion in a spherical field of same magnitude, and we consider the same metal ion is placed in a crystal field of appropriate symmetry, and the energy change that is observed when you place the metal ion in a ligand environment of appropriate symmetry, so octahedral, square planar, trigonal, bipyramidal, etc. So the energy change that is called the crystal field stabilization energy, right? So in general, CFAC should be in general CFAC for in most of the books they consider as the energy, if I call it octahedral complex, energy of the octahedral complex, right, minus energy of the say spherical field, right, energy of the spherical complex, right. So that is the energy difference. It is called the crystal field stability. If the energy is negative, right, then it is stabilized. If the energy is positive, it is destabilized. But this was the earlier nomenclature, but very often modern books use the opposite nomenclature. That means ES minus EOH, right. So that means the energy difference between the spherical minus this, and if it is positive, because in this nomenclature more negative value means more stabilization, but modern books call it stabilization means in a positive sense. So how much it is stabilized? So you take the energy gap between the spherical symmetry thing, or sometimes isolated gaseous ion, and the octahedral field, or say octahedral or tetrahedral or square planar, whatever the symmetry of the complex may be, right? And you find out that compared to the octahedral symmetry, or on going to the octahedral symmetry, how much it is stabilized. So here the value will be positive. More positive the value is, more is the stabilization. And here the value is negative. In this case, if I take this kind of subtraction, then in this case more negative the value, more is the crystal field stabilization. But modern books write crystal field stabilization energy in a positive sense. That means they are taking the energy gap between the spherical symmetry molecule, spherical symmetry metal ion, minus the metal ion in a octahedral or tetrahedral or square planar or say trigonal bipyramidal geometry, and they find out how much positive this value is, because this value will be higher, this value will be lower, right? Because of the crystal field splitting, the energy will be lower here, and so this gap is called, in a positive sense, it is called crystal field stabilization energy. So just as you know, electron affinity or affinity energy has got two nomenclature, right? Some people call it positive, some people call it negative. So here also there are two nomenclatures, but now this is more accepted. Crystal field stabilization is positive, and in order to calculate crystal field stabilization energy, what do you have to what do you have to calculate? What is the what with respect to spherical field? What is the stabilization? So you find out the energy of the system. So you can consider this as zero. Yes, can be considered arbitrarily as zero. So you consider with respect to spherical field, what is the energy of the system in presence of the octahedral or tetrahedral or square planar field, and then take negative of that, and that will be a minus of that, and that will be your save AC. Okay, so see how to calculate save AC. Suppose here D1. So energy of the system is minus 4 dq. So we shall say CFAC. So if I say CFAC, we shall call it 4 dq. Right. If you have a D2, so you have two electrons in the T2G. So minus 4, 8 dq. So CFAC will be called as 8 dq. So energy of the system is 8 dq with respect to spherical field. Energy of the system is lowered by 4 dq. So now it is minus 4 dq. Here it is minus 8 dq. And so CFAC will be 4 dq, 8 dq, 12 dq, etc. So in this way, crystal field stabilization energy is determined or defined. That means with respect to spherical field, how much it is stabilized, and why it is stabilized, its energy must be lower than the spherical field, and that's why it is stabilized. So we take the negative of the energy of the system, and that gives you the crystal field stabilization energy. Now for D1, D2, D3, calculating CFAC is not difficult, because the energy of the system can be easily calculated unambiguously, and so you can define the corresponding CFAC. Now when you go to D4, there may be D4 to D7, we have ambiguous case, in the sense for D4 you may be high spin configuration where 3 electrons are in the T2G and 1 electron in the EG. So that means here we have a T2G3 EG1 configuration, or you may have a T2G4 configuration, right? So in this configuration, the energy is minus 12 plus 6, right? So minus 12 plus 6. So that means minus 6 dq. Energy of the system is minus 6 dq. And so the save AC is plus 6 dq. Now in this configuration, you see 4 electrons are placed in the in the T2G orbital. So energy is minus 16 dq. But here we have to add a pairing energy. Why? Because when you have a spherical field, when there is no splitting of d orbital, when all the T2G or all the d orbitals are degenerate, then if you fill up D4, 1, 2, 3, 4. So there were 4 unpaired electrons. Now you have forced a pairing. So compared to spherical field, there is one additional pairing here, and that additional pairing, and this pairing energy is positive. So that additional pairing you have to give it here. So here the energy of the system is minus 16 dq plus P. So if I ask you what is the CFAC, CFAC will be minus of that. That means 16 dq minus P, right? This is the energy of the system. Here we have written the energy of the system, right? And then minus of that. So crystal field stabilization energy is 16 dq minus P. Now if I go to D5 again, you may have 5 electrons being put here, or you may have 5 electrons being arranged here. This is called the high spin configuration, T2G3 EG2, and here we have T2G5. If you have T2G3 EG2, here it is 3 minus 4, that is minus 12 dq. Here it is 2 into plus 6 plus 12 dq. So minus 12 dq plus 12 dq, they cancel out, and so CF energy of the system as well as CFAC is 0. On the other hand, in this case, here we have 5 into 4 minus 20 dq, and for a D5 system in a spherical field, you have 5 unpaired electron. Now you have 2 paired, and so because of the, so you have to add 2 pairing energy plus 2p, right? Similarly, if you go to D6, if you have D6, you may have a T2G4 EG2 configuration. That means after getting D5, you add one more electron to the T2G. So this is the T2G4 EG configuration, or you may have a T2G6 configuration. Now in the T2G4 EG configuration, what is the total energy? Energy is here, there are 4 electrons, so minus 16 dq, right? Yes, minus 16 dq, and here we have plus 12 dq. So 4 dq minus 4 dq is the energy of the system. So this is the energy of the system, and so CFAC will be plus 4 dq. Now you may question me, sir, here is a pairing, but why we are not why we are not adding pairing energy? Because we have to compare the pairing with respect to spherical field. So in the spherical field, if we have a D6, there is also a pairing. So in the spherical field, there is one pairing, and here also there is one pairing. So that means on going from spherical field to weak field, there is no additional pairing. You have to add pairing energy to the CFAC only when there is additional pairing with respect to the spherical field. So since in case of weak field, there is no additional pairing, so we are not adding pairing energy. Now in case of low spin, you find that in the D6 configuration, we have 6 electrons, so 6 into minus 4, minus 24 dq. The energy of the system is minus 24 dq. And though there are 3 paired electrons, but comparing with the spherical, in the spherical system there was one pairing. In the strong field case, that means low spin case, we have 3 pairings. So what is the additional pairing? 2 pairings are additional. So we are adding plus 2p as the additional energy. So please remember, students make a mistake here. They just look it here and they add 3p. 3p is not, you have to always compare pairing with respect to spherical field. So first of all, you have to draw the corresponding spherical field diagram and compare what is the additional pairing. So in case of T2G6 configuration, compared to the spherical field, there are 2 additional pairing, whereas there is no additional pairing here. So here there will be no pairing energy added. Here 2 pairing energy will be added. And then in case of D7, we have either T2G5 EG2 as it is here, right? And so you can calculate the energy, it will be equal to minus 8 dq. And so the CFAC will be 4 dq here and CFAC will be 8 dq here, right? Now in this case, we have a T2G6 EG1 configuration. So it is 6 into minus 4, that is minus 24 plus 6, right? So minus 18 dq plus, for D7, you see, when we have a D7 in the spherical field, we have this thing. So here, with respect to spherical field, only there is one additional pairing. So we have to add only one pairing, right? So here, as you can see it here, so here there are 2 pairing. That's why in the spherical field also there was 2 pairing. That's why we have not added any pairing energy here. But in this case, here there is 3 pairing. But in the spherical field, we have 2 pairing. So we have added 1 pairing energy here, right? So energy of the system is minus 18 dq plus p. And that's why the corresponding CFAC is plus 18 dq minus p. Now, when you go to D8, D9, and D10, there is no ambiguity. There is only one possibility, T2G6 EG2, and you can calculate the energy of the system as minus 12 dq. And so the energy of the CFAC will be plus 12 dq. Here for D9, it is minus 6 dq, and so CFAC will be plus 6 dq. But we have to take more about this, talk more about this later, because there will be additional complication due to Yankeler effect. And we have the D10 where we have no crystal field stabilization because energy of the system is 0. Right. So this is how you calculate CFACs, and with respect to CFAC, you find out which one is more stable, whether lower crystal field is, or whether the strong field case is more stable or weak field case is more stable, or in other words, whether high spin case is more stable or low spin case is more stable. Now, if you compare this D4 to D7, say in any case, D4 for instance, you see in the low spin cases, in the low spin case it was 16 dq minus 16 dq plus P. Here it is minus 6 dq. Or CABC, here it was 6 dq. Here it is 16 dq minus P. So if I calculate, or if I say the energy gap between, say, low spin minus high spin, right? So it is equal to 16 dq minus P minus 6 dq, so equal to 10 dq minus P. And fortunately or surprisingly, if you subtract anywhere, it will be always a contest between 10 dq and minus P. So you can see here whether low spin will be more stabilized or high spin will be more stabilized. It depends. It depends on the 10 dq minus P this factor. 10 dq minus P this factor. If your pairing energy is more than 10 dq, if pairing energy is, suppose when pairing energy is more than 10 dq, then this is negative. This is negative, right? This is negative means high spin has got lower energy than the low spin. That means high spin. So in this case, high spin is more stable, right? High spin high spin is more stable than low spin. On the other hand, if 10 dq is more than P, right? If 10 dq is much more than P, then this is positive. So that means low spin stabilization energy is higher, and as a result of this, the low spin complex will be favored. So whether you will get a high spin complex or low spin complex, it depends on the fight between 10 dq and P. If 10 dq crystal field is much lower than pairing energy, then pairing will not occur. In other words, if the crystal field cannot compensate for the additional pairing, in every case you will find that when we go to the low spin configuration, there is some additional pairing compared to the high spin case. So whether it will be high spin or low spin depends on this energy gap and the pairing energy. If the pairing energy is larger than the energy gap, then the stability it gains by putting one more electron in the T2G orbital cannot be compensating the extra pairing energy. And so the high spin configuration will be more stable. On the other hand, if 10 dq is much larger than P, then the pairing energy needed can be more than compensated by the extra stabilization gained by putting one electron in the T2G orbital. So whether you get a low spin configuration or high spin configuration, it depends on the fight in energy between the crystal field splitting and the pairing energy. If crystal field splitting is larger, in that case, the energy required for pairing will be more than compensated by the crystal field. On the other hand, if the crystal field is weaker, then the energy required for the pairing cannot be provided by the crystal field stability, additional crystal field stability, and as a result of this, pairing will not occur and the high spin system will be more stable. So whether high spin system is more stable or low spin system is more stable, that depends on this. This is actually, we are talking about the CABC, right? CABC of the high spin, we are comparing CABC of the high spin and CABC of the low spin. So if I compare the CABC of the low, if I take the difference between the CABC of the low spin and CABC of the high spin complex, then if the CABC of the high spin is greater, and that will be greater when 10 dq is more than P, then low spin complex will be more favorable. On the other hand, if the CAVC of the high spin complex is greater, that will happen when P is more than 10 dq. In that case, you will find that the high spin complex is more stable. So high spin, low spin, whether a complex will be high spin or low spin, it will be always a fight between 10 dq and P. Now you can see here the energy gap is actually 20 dq plus 2p minus 2p, right? So again, it is actually fight between 10 dq and P, or its multiplication. So here it will be 20 dq minus P. Here it will be again 10 dq minus P, etc., etc. So ultimately here again 20 dq plus 2p, and here it is 0. So that means ultimately, so if you take crystal field stabilization energy, it is 20 dq minus 2p. So 20 dq minus 2p means it is actually a contest between 10 dq and P. So 10 dq and P, their contest will decide whether you get a low spin or high spin. If 10 dq is larger, then you get the low spin. If P is larger, you get the high spin. Next question is, what is pairing energy? What contributes to the pairing energy? Now, pairing energy has got two components. What are the components? One component is Coulombic repulsion. That means we know orbital. What is the definition of orbital? Orbital is a region of space where there is high probability of finding an electron. So if you put two electrons in the same orbital, that means if you are putting two electrons in the same region of space, and electrons being negatively charged, if the two electrons are put in the same region of space, they will repel each other. So when you try to pair it up, that means you are putting two electrons in the same orbital, so they repel each other, right? And this repulsion will be greater if the orbital size is smaller. This repulsion will be relatively less if the orbital size is larger. Just as if you have a room, for instance, in your hostel, and you have to have two persons allotted in the same room, then greater the room size, obviously you will feel the two students will feel more comfortable. On the other hand, if the room size is smaller, then there will be more collision between the two persons. So here also, when you are putting two electrons in the same orbital, so as the orbital size increases, the electron-electron repulsion decreases. So 3D size is smaller, so their electron-electron repulsion is highest, and 5D size is larger, so there the Coulombic repulsion component of the pairing energy will be lower. The other component to the pairing energy is the loss of exchange energy, right? What do you mean by loss of exchange energy? We have exemplified it by the example here. Suppose we have a D6 high spin. Now in case of a D6 high spin, as you can see here, so 1 2 3 4 5, we have five electrons with upspin, right, and one electron with downspin. So since 5 electrons are with upspin, they can undergo exchange between themselves, and this exchange phenomenon. Whereas Coulombic repulsion is a classical phenomena, the exchange energy, that is a quantum phenomenon, and it is found according to quantum mechanics. Just as you have learned in resonance, more the number of resonance structure, greater is the stability. Here we can say more the number of exchanges possible, more is the stability. So when you have 5 electrons which can exchange between themselves, so we have, what are the possible exchanges? 5C2, and that is equal to 10. So 10 number of exchanges between the upspin electrons are possible. Now when you go to the low spin configuration, then you have this T2G6. Now in the T2G6, we have 3 electrons with upspin and 3 electrons with downspin. So for 3 electrons with upspin, we have 3C2, that means 3 number of exchanges possible. 3 electrons with downspin, again 3 exchanges possible. So total, you can exchange the upspin electron 3 times, and you can exchange the exchange the opposite electrons 3 times. So it is 6 times, right? Downspin electron 3 times, so 6 times. So compared to the spin free path, that is the high spin configuration. In the low spin configuration, we find the number of possible exchanges decreases. Now I have told you, as the number of exchange increases according to quantum mechanics, more energy is released. So when you go from the high spin to low spin configuration, in case of D6 like this, we find the number of possible exchanges decreases and this leads to decrease in stability of the system. So laws of exchange leads to laws of stability. So pairing energy has got two components. One is the increase of electron repulsion due to housing of two electrons in the same orbital, and that causes electrostatic repulsion. The other is that pairing of electrons leads to loss of exchange energy, and loss of exchange energy leads to decrease in stability. I shall stop it here. So in the next class, we shall discuss the high spin, low spin equilibrium problem, and then we shall go to the Untitled effect. Thank you. Any question? We have 5 minutes left, so you can ask any question.
Hello, sir.
Yes.
Is there any practical for inorganic?
See, it has been decided that from 24th of March or something like that, you will be coming to the physically, right? So after mid-semester, we shall see what are the practicals that will be there in the inorganic, right? Okay.
Okay, sir. After
Because
the practical, we are
after
asked
the
to
after
make
the
the
mid-sem,
notes.
after the since will be coming physically after mid-sem, so no use of showing these videos etc. because since you will be coming physically, so we shall try to see what happens then. Okay.
Okay, sir.
Any other question? Okay, if you don't have any question, I can leave.
Thank you, sir.
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 Thank you, sir.